Hello class. So today we're going to be talking about triple integrals. So what exactly is a triple integral? A triple integral is a method of finding volume by taking the integral of a function with three variables. So one way you can define a triple integral is as follows. You have your three integrands, the function of three variables, and like I said earlier, it's a method of finding volume, so it will be respect to volume. So we can use this triple integral to find the volume of a solid region bound within the xyz axis. And so our first problem, we're going to be working with a rectangular box. So we have our xyz axes, so x, y, and z. There will be a rectangular box within these axes. And this box, we'll call it B for box. And one way you can notate this box is to say that B, the solid region, lies within the x, y, z axis. So it is a function of three variables. And within the x, in the x distance or the x-axis, it varies from A to B. In the y-axis, it varies from C to D. And in the z-axis, it varies from R to S. And so we have our box defined here. So when we take triple integrals, the best way to visualize how to take the triple integral of any kind of solid region or any kind of three-dimensional shape is to take partitions or separate the shape into little small boxes. And it's kind of like a Lego. So if you could visualize this box being separated into each individual little box. With these little boxes, if we sum them up within the change of x, within the change of y, and within the change of z, we will get the volume. So another way to write the volume is delta v equals the change in x, change in y, and times the change in z. And since I stated earlier, the x-axis varies between a and b, or is bound between a and b, y is bound between c and d, and in the z direction it's bound between r and s. We can all agree that the volume can also be written as a comma b times c comma d times r comma s. And since this box B, rectangular box B, is bound by these values, the triple integral for finding the volume of this box B can also be written as this. The integral from A to B, which is in respect to x here, and then the integral from C to D, which is in respect to y. And then the integral with respect to z, which is from r to s. And so this is the general concept of using triple integrals to find the volume of any kind of region in the xyz axis. In this case, it's a rectangular box. So with that same concept in mind, we're going to be doing a sample problem, and keep in mind that we're still working with rectangular boxes as of right now. And so the problem says evaluate the following, which is the triple integral of 8xyz dv, where the box B is bound, where the x-axis of the solid B is bound between 2 and 3. In the y direction, it's bound between 1 and 2. And in the z direction, it's bound between 0 and 1. And so when you get a problem like this, it would help to draw the actual box. So that is what I'm going to do first. So we have our XYZ plane here. X, Y, and Z. And in the X direction, it's bound between 2 and 3. There's 2. There's 3. In the Y direction, it's bound between 1 and 2. There's 1, there's 2. And in the Z direction, it's bound between 0 and 1. So that would be 0. That's 1. And so you can kind of think of it as if it just goes up 1 value here. Oops. So it kind of looks like that. It's a pretty bad drawing. It's just a little box. And so we're going to take this box, I'll just redraw it down here. And we're going to separate it into little partitions, and we're going to sum up those partitions of little boxes within the rectangular box to find the volume. So first, we're going to set up our triple integral. And so we can think of this, the region bound by the rectangular box. That's A, that's B, that's C, that's D, and that's R and S. And as we said earlier, the volume can be written as the triple integral from A to B, C to D, and R to S, a function of 3 variables with respect to X, Y, and then Z. And so based on this concept, we're going to just move these numbers here, and here is the actual function of the shape. And so we're just going to plug these in. And so the volume is now the integral from 2 to 3, the integral from 1 to 2, that's the y, and the integral from 0 to 1, that's the z, of this function. So that's 8x, y, z, with respect to the volume, so dv. And so that's how we set up the triple integral to find the volume. And when we're working with triple integrals, or even double integrals for that matter, the order of integration is very important. It really does not matter which way you set up the order of integration, as long as you follow that same setup throughout the evaluation of the triple integral. And since I already have my regions bounded here, x, y, and then z, that's going to be my order of integration. So I'm first going to integrate with respect to x, then y, then z. So this expression here can be rewritten as this. That's just the same integrand here with the bounds. This is the function 8xyz. And first I'm going to integrate with respect to x, so dx, then respect to y, dy, and then respect to z, dz. Again, this part here, the order in which you integrate, it can be dy, dz, dx, or dz, dx, dy. It really doesn't matter, especially when we're working with cubes or rectangular boxes. But As we work with more complex shapes such as paraboloids or other abstract figures, the order of integration may be important because it'll be easier to integrate in one way than another. But since we're working with a box here, it doesn't matter. So I'm going to be integrating with respect to x, then y, then z. And so we're going to integrate this here. So we first start with the inside, and we treat all other variables except x as a constant function, as a constant. And so if we integrate this, we get so it'll be x squared and then over 2, so that cancels out to 4. So that'll be 4x squared y z from 2 to 3, and then dy dz. And now we do top minus bottom here. So we do we plug in 3 for x. So that's 4 times 9, so that's 36. Minus, we plug in 2 for x. 2 times 2 is 4, times 4 is 16. And then y z should be 36 y z. dy dz, and then the rest of the integrals here. 1. So we can simplify this to 0 to 1, 2. So this will be 20 yz dy dz. And so we do the same thing here now with respect to y. And so if we integrate this, that'll be, just erase all this up here. Bring this up here. If we integrate this, that'll be 20 y squared over 2. So that's just 10. And then z from 1 to 2, and then with respect to z. And so that can be written as 1, 10 y squared z, 2 to 1 dz. And so using the fundamental theorem of calculus, we're plugging 2 and then subtract that by plugging in 1 for y. So that'll be from 0 to 1. 2 squared is 4 times 10 is 40z minus 10z dz. And so that can be, again, simplified to integral of 0 to 1, 30z dz. And we do it again, finally, with respect to z. And so we take the integral of this is z squared over 2, that's 15. Can be rewritten as, oops, no, I'm going to go here. 15z squared from 0 to 1. Again, we use fundamental theorem of calculus, and that'll just be 15 minus 0, which is 15. And so that's our final volume. So now that we've evaluated the triple integrals for solid regions, such as rectangular boxes, we have a new problem here, and it says evaluate the triple integral of 2x dv, where E is the region underneath the plane 2x plus 3y plus z equals 6 that lies in the first octant. And to kind of help visualize the plane and the region underneath that plane within the first octant, I've drawn it out right here. In the x direction, it goes up 3 values. In the y direction, it goes up 2 values. And in the z direction, it goes up 6 values. And so that plane right here is symbolizing this equation right here. 2x plus 3y plus z equals 6. Before we evaluate the integral, we need to set this up. And in order to set this up, we have to find the limits of integration, which are the upper and lower bounds for each of the three integrals. And so to help find the limits of integration for in the x-axis and the y-axis, what you can do is draw an xy graph of this region right here. And so that graph will look like this. So in the x direction it goes up 3 values, and in the y direction it goes up 2 values, as seen here. And so we'll just draw this in an xy plane, and that's the region given by that. And so to find the limits of integration for the x and y planes, or the x and y axes, you can find the line. So this line here, this line, that line right there, or this line here, you can find the equation for that line and use that to set up the bounds, the upper and lower bounds for the integrals. And so this line can be represented as y equals negative 2/3 x plus 2, or it can also be written as x equals negative 3/2y plus 3. And so using either of those two equations, we can use them as bounds to set up the triple integration. And now to set up the integral, we have to determine the limits of integration, which are the upper and lower bounds of the integrals. And I've decided for this particular problem, I'm going to be integrating with respect to z first, then y, then x. And if I'm going to integrate with respect to z first, I have to find the limits of integration for the z-axis first. And so that'll be given by the equation So the first integral with respect to z, the lower bound is going to go from when z equals 0 to when that value reaches 6. And so that will be given by the equation z equals 6 minus 2x minus 3y. And that's derived from this equation up here, which is the region of the equation of the plane. And so that's my first limit of integration with respect to z. So then we write the rest of the equation. So that's 2x, and then with respect to z, so that's dz. And then the rest of the equation, we'll call that dA. And now using basic integration, since we're integrating with respect to z first, we're going to leave any other variable constant. So this 2x will remain constant. And so the integral of dz is z. So this can be rewritten as 2xz from 0 to 6 minus 2x minus 3y dA. But now dA can be rewritten as dy and then dx. As I've decided up here that I'm going to integrate first with z, which I already did, and then with respect to y, then x. Now using the fundamental theorem of calculus, I can substitute in these lower and upper bounds for z, and that'll give me the equation 2x, 6 minus 2x minus 3y, dy dx. And now that I have my x and y variables here, I can now determine the limits of integration for the rest of the region. So first with respect to y, and then x. And as I showed you earlier here, this is the xy plane. It's kind of the bottom surface of the region E. And so using the line here, which we found earlier, we can determine the lower and upper bounds for y with respect to y. So for the y, in the y direction, it'll vary from 0 to negative negative 2 over 3x plus 2, and that's this point up here. And then it'll be with respect to x, and so that'll be from 0, and x goes to 3. And so that's the rest of the setup for the triple integral. We've already integrated with respect to z up here, and then this is the rest of the setup for y and then x. There's this up here. And now using integration and FTC, our final expression down here should be 1/3 x to the 4th minus 8 over 3 x to the 3rd plus 6x squared from 0 to 3. That's with respect to x. Now using FTC, plug in 3 and 0 for x, and the final answer is 9. So triple integrals are fun and all, but you might be asking yourself, what kind of real-world applications are there for these crazy triple integrals? Well, one area of study that uses a lot of calculus is physics, and you can use triple integrals to find the center of mass for a particular shape or object. And so to demonstrate this real-world application, we will be finding the center of mass of a unit cube. So I will draw the unit cube right here. Oops. Very good. As follows. And they'll all go out 1 unit. So it'll look kind of like this. Like that. And so that'll be our unit cube, and they all go out 1 unit. And the problem is, find the center of mass. Center of mass of the unit cube, here, this unit cube, given that the density at point x, y, z, so at any given point within the cube, is proportional to the square of its distance from the origin. And so next, we're going to need to find the expression to determine the center of mass for this cube. So in order to find the center of mass for this unit cube, we have to remember the equation, the lovely equation, density equals mass over volume. And here they give us the expression for density. And so because density at point x, y, z is proportional to the square of the distance between the origin and that particular point, that expression can be written as this. P of x, y, z, so that's the function of 3 variables, is equal to some constant times x squared plus y squared plus z squared. And so this expression here shows us the shows us the density of any given point within the unit cube. And since we know that density equals mass over volume, we know that mass equals density times volume. And we've determined earlier that we use triple integration to determine the volume of any kind of shape or object in 3 dimensions. And so that triple integral can be expressed by this volume, here, and we've determined the density with the given information. So that density So the density here will be expressed by this equation. And so using all of this information, we can determine that mass is equal to the triple integral, which is essentially the volume, of the density, which we determined here is k times x squared plus y squared plus z squared. And then we're going to integrate it, I don't know, dz, dy, and then dx. And so this is our expression for mass, because we know that mass equals density times volume, which is determined by the triple integral. And so in order to determine the limits of integration, or the lower and upper bounds of each x, y, and z axis, we can take a look at our graph. And I said earlier that all of these points go up to 1. And so our lower and upper bounds for each z, y, and x will just be 0, 1, 0, 1, and 0, and 1. And so this is the expression for finding the center of mass of the unit cube. Now the fun begins. So we're going to evaluate the expression that we determined earlier, where mass is equal to the triple integral of k times x squared plus y squared plus z squared dz, dy, dx from 0 to 1, 0 to 1, 0 to 1. And so first we can take the k out since it's a constant, so we can remove that from the integral expression, so that can also be rewritten as k times the triple integral of x squared plus y squared plus z squared dz, dy, dx from 0 to 1, 0, 1, 0, 1. Now we're going to integrate with respect to z first, so we're going to hold x and y constant. And so that'll be written as the expression here as follows. So that'll be x squared z plus y squared z, which is also x plus y squared times z plus z to the third over 3. And then dy, from 0 to 1, dy, dx. And the bounds here have not changed yet. And so if you use FTC and plug in 1 and 0 for z, you'll get k x plus x squared plus y squared plus 1/3, and then dy dx. And so again, you're going to integrate with respect to y, so you hold x squared constant in this case. So that'll be equal to k times the integral of 0 to 1 of x squared y plus y to the third over 3 plus 1/3 y from 0 to 1 with respect to x. And so again, using FTC, plug in a 1 for y, subtracted by plugging in 0 for y, you get k integral 0 to 1 x squared plus 1/3 plus 1/3 dx. And so that's also equal to k times the integral of x squared plus 2/3 dx. And now you're just going to integrate with respect to x. So that will be k times x to the third over 3 plus 2x over 3 from 0 to 1. And then if you plug in, if you use FTC again and you plug in 1 and then subtract it by 0 for the values of x, you'll get k. So we've determined that the mass of the cube is equal to k. And now using a little physics, which isn't taught in multivariable calculus, unfortunately, we know that m of yz, which is the moment of inertia about the yz plane, equals to the mass times x bar. And so this can be rewritten as mass, which is k, we found that earlier, times x bar, which is given by the expression, the triple integral, excuse me, of x times x squared plus y squared plus z squared dz dy dx. And that's all from 0 to 1, 0 to 1, and 0 to 1. And so since now we've set up this equation using a little bit of physics, we can use calculus to evaluate this integral. And so that can be rewritten as m of yz equals k times the integral from 0 to 1 of x times x squared plus 2/3 dx. And now we can integrate this. And so that's equal to k times, and I integrate this with respect to x, you'll get x to the 4th over 4 plus x squared over 3 from 0 to 1. And you'll find that that is equal to 7k over 12. Now, we're going to use this, plug this back up here. And so, because x bar is equal to m of yz over the mass, we've determined that m of yz, which is the moment of inertia about the yz plane, is equal to 7k over 12 over the mass, which we found earlier, which is k. And so the k's cancel out, and so we know that x bar equals 7 over 12. And that is the center of mass of the x value within the unit cube. So then we know that the center of mass for the entire unit cube can be written with the expression 7 over 12, comma 7 over 12, comma 7 over 12. And so that is the center of mass for the unit cube. And so we can see that we can use triple integrals to determine center of mass as well as moments of inertia for solid regions within a three-dimensional space. So that is it for triple integrals. It did seem daunting at first, even for me, but as you can see, it's really not that bad. Thank you so much for watching. I hope you learned a lot about triple integrals. Thank you, Ms. Mack, for being such a supporting and fantastic teacher this year. You really made Calc PC very enjoyable. I'll be looking forward to multivariable calc next year with you. Thank you, and goodbye.